Hola, ¿qué tal? Please come in, everybody. This is about joint work I did with René Pickhardt, whom you all know, I'm sure. He unfortunately couldn't make it here. But we've all been sitting for a while, and I want you to help me, to join me in a scientific experiment, please. Let's see if we can do that. Yep. Stand up if you have used the lighting in work, please. Real payments. No, just custodial is fine, but at least the other part should have been a different wallet. So there should be a real Lightning Network have happened. There's actually some people here who have never used Lightning. Interesting. You're just lazy. All right. That's great. No. Please stay. Not yet. Are you? Not yet. I want to only the people to sit down who, in every Lightning payment they ever did, it always worked. Oh, that's interesting, right? Isn't that? I think. Oh, that's the wrong. Okay, that's not the right slides. But never mind. Okay, I think there's room for improvement here, don't you? All right, thanks. Please, now you may sit. Now you see the problem, right? Our question is why do payments fail? I mean, there might be a lot of reasons why payments fail, right? It might be trivial. It might just be you don't have any internet. That happens, right? And there are some more. But what René did, like about 2 years ago, he got very interested in the last reason here, which I think is a very important reason because it's kind of intrinsic to the way the Lightning Network is designed. And that's missing liquidity, right? Because the Lightning Network works by forwarding payments via multiple hops and via multiple channels. And it's a design decision in the Lightning Network. It's very important that you don't know the balances in these channels. You don't know on which side they are, right? For two reasons. One is scalability, because otherwise we would just broadcast everything to everyone and we would have another blockchain. And the other is privacy. So this is not a choice. This is not an option. We can't know the balances in every channel. So there is, by design, uncertainty about these balances. So we call this uncertainty of liquidity as well. And René's idea was, what about if we have uncertainty somewhere, there's a mathematical way to talk about uncertainty. And we call that probability. And what you do is you model the uncertainty and you give values to it and say, okay, how probable is it that certain things happen? And that's what's work that René did with other co-authors. And that came out in March, I think. And this is the Lightning Network. Now, of course, it's not the Lightning Network, but it's our toy Lightning Network. And you got to get used to this graph because this is the one I will use the whole talk. So that we have nodes, we have channels between the nodes, and then the numbers there are the capacities, right? And just imagine it's Satoshis. It's very, very small channels here because it's a toy example, right? And our question is, how do we deliver some sets from S, from the source, to D, to the destination? There are several ways to do this. And notice that you might initially have been jumping to the thought, okay, we have to go via some path or something, because that's what the implementations do today. But generally, notice that this is a very general transportation problem. It's something we call a flow problem, because there might be several ways that things might flow through this graph, right, from S to D. There are several possible ways, and we might use several of them at the same time. And what this transportation or flow problem, it has some properties, very simple properties, right? We have an amount that we want to transport from S to D. We know the amount, that's the amount we want to pay. And let's abstract from fees here for a moment, because it's simpler to talk about it then. So then, if we abstract from fees, then the amount that comes from S is the same amount that has to go into D, right? But for every other node in the network, whatever routes we choose, there's this very simple property. The amount that goes into the node, say X, is the same amount that goes out of the node, say to B and to Y combined, right? It always has to hold. Again, we're not talking about fees, right? But we could talk about fees, but it just makes things more complicated. And that's the mathematical definition of something called a flow. Everything that goes in has to go out except for the source at the destination. Very simple. But let's start with the 1 Satoshi case. We would just want to transport 1 Satoshi. Though. So if it's 1 Satoshi and we assume we don't know anything about millisatoshis and stuff, we can split it. So the solution here will be a path. And I said we want to talk about the probability, right? We want to talk about the uncertainty. We know the capacity of the graph of the channel between A and B, for example, is two sets. But we don't know where these 2 sets are. A might have them all, or B might have them all, or they might be split, right? So what is the probability that A can route 1 set to B? Think about it. 2/3. Why? Wow, that's really good. It's really easy, right? If you haven't figured that out, I'll help you. That's the formula. Really scary, right? A scary formula. No, it's not. This is really high school calculus, high school probability, right? It's really easy because the thing is we have a capacity of 2. That means we have 3 possible states that this channel might be in, right? A might have 0 sets or 1 set or 2 sets. 3 possible states, all right? That's the denominator down there, C plus 1. And the amount that we want to route is 1. So how many of these states are good for us? Well, if A has at least 1 Satoshi, then we can route. But if he has no Satoshis, then we can't route. So there's 2 of these 3 states are good for us, which is why you were right. The solution here is 2/3, right? 2/3 is the probability that we can route from A to B. And we can do this calculation for all of the channels. And if we do, there's something, I made some assumptions here, right? If you paid close attention and you have actually paid attention in high school, you will notice I've made some assumptions. One is, all of the states that I just talked about are equally probable. We call it a uniform probability, uniform distribution. And that's a big assumption. But René and his colleagues actually measured the graph, the actual Lightning Network, and said, okay, it looks as if that's a pretty good assumption. It works pretty well for something called like the active core of the network, right? That means nodes that people actually route with, and not just somebody installed a node on a smartphone and never used it, right? But for those, I think uniform probability distribution is a pretty good assumption. And that's another big assumption, is channels are independent, which means the probability that I can route from A to B is independent of the probability that I can route from Y to D, which is all a big assumption. It's not true, of course, right? In reality, it's not true, but it's still, I think, a pretty valid assumption because lots of changes happen in the Lightning Network all the time, and if you sum these all up, there are some probability laws that say, okay, this might look similar to independent distributions. And it turns out if we do this, it works pretty well. And otherwise, it would be very hard to model. So yeah, we wanted to question, so how probable is it then that we can route from S to D on one path? And there's a basic principle here, that payment delivery is successful only if every used channel is successful, right? In a path, that means, okay, of course, right? We only succeed if all the channels on the path succeed. If we use multiple paths, the same thing holds, right? Every channel that we use in the payment has to succeed in order for the whole payment to succeed. It's a little more subtle there because we could have a partial success if one path succeeds but others don't, and then we have a smaller problem and we learn something about the graph, but still, the basic principle holds, and I just told you, we assume that all these channels are independent. So again, high school math, what's the probability for all of these channels to succeed? We just multiply them, right? It's just the product of all these probabilities. So the upper path here is just if you multiply 2/3 and 2/3 and 4/5, we get 0.35555. And now we can actually look at all these paths and say how probable is it to route around them. right? The lower one, turns out, is a little worse. It's 0.35. And then there's just one more here, and it crosses the middle, and it turns out that's the best one. It has 0.36. It's a 36% probability to succeed. So in this example, okay, it's a toy example. These are very close together. In the real network, they might be very far apart. And it might make a huge difference which part we choose. And yeah, and René and his co-authors showed that theoretically this should improve things. And just, as I said, it was in March, but now like 2 weeks ago, Sea Lightning implemented this, or a version of this, and it turns out, yes, it actually makes things better. People actually report that it just works better, and it was a very, very simple change. It's just basically 2 lines in the code changed, because all we do here is change the cost function, right? Because what Sea Lightning and all the other implementations now do, they look for a cheapest path. But cheap, you know, it depends on your cost function. Right? Now, for a long time, this has only meant fees. But now it turns out there's a basic trick where you can turn probability, like maximizing probability, into minimizing some kind of cost. What you do is you just take the negative logarithm of the probabilities, standard trick. So then you can make uncertainty costly in a way. And that's very simple to implement, and actually, as I said, Sea Lightning did this. It helps. I just heard L&D has a pull request right now. I think it opened yesterday or something. They want to do the same thing. Actually helps. And there's still room for improvement, I'm saying. Because, and that's where it gets interesting for me, that's where I get excited about this. This probabilistic framework, it looks very simple, right? It's a basic thing. It's just somebody wrote up the actual probabilities, high school math. But I'm arguing that this is very important because it allows us to talk in a proper mathematical model about uncertainty. And that allows for several things. For example, we can learn from previous attempts via the uncertainty network, which is the network where, as I said to you, where the probabilities are, where we know how probable is it to route in one channel. And if we learn something, for example, we had a failed attempt and the two first channels in the route worked, but the third didn't have the capacity, then we have learned something. We have learned, oh, yes, this amount can definitely be routed on these two channels, the first channels, but it definitely cannot be routed on the third channel, right? And we can update our probabilities, and we have a clear mathematical model to talk about these things. I mean, updates have been done before by the implementations, but they all do some kind of ad hoc thing. They try to, oh, this might work, but this is a clear mathematical model where we can actually talk about these things. And a very similar effect is we can talk about privacy guarantees, because uncertainty is just another word for privacy, right? If we know we have uncertainty about what's in a channel, then we know there is a kind of privacy. And if we can describe the probabilities here, then we can make and we can say things about what, say, a protocol change or something changes about the privacy in the network. So that's another advantage. And of course, we could use different probabilities. We could not just use the capacity thing here. We could model in different things. We could say, oh, we know this node here is very reliable and this one isn't. That's pretty much what the implementations do, or some of them do right now already. We can add these, right? There's a lot of things we can do with probability. But the thing that I am most excited about is we can apply this principle to multipart payments. Because the question that multipart payments always give us is to split or not to split, right? And what I just told you, that the capacity here plays a big role, it gives us some easy observations, right? One is smaller payments have a larger success probability. So yeah, that's an argument for splitting, right? But on the other hand, more channels, if we use more path, we get more channels. And then the probability drops exponentially because we have to multiply all these probabilities, right? So that's an argument against splitting. So should we or should we not split? And also, if we, as I hinted at that before, if we do a multi-part payment and one path fails but another doesn't, we have learned something and we can use this in our next round of trying, right? So that's another argument for multi-part payments. But how do we actually get at a good split? And there hasn't been an answer to this before. And that's what René and I looked at during the summer. And we published this paper, I think in July. I'm not sure. And that's what I hope. Won't work. Yep, there we are. Okay. Oh, the 2 Satoshi case, yeah. Let's look at the 2 Satoshi case. And what is the best way to transport 2 sats? And notice this is the same network as before, the same lighted network. It looks just shittier. But in math, we abstract from properties like shittiness and just assume it's the same network, right? So, okay. So the same thing, and the question is how to route 2 sets. And that's a more difficult question, it turns out, because there are more ways of doing it. And we could just use, there's actually one path here that could support as one path or two Satoshi payment. It's the upper one, right? And if we use the path, it turns out the probability for this succeeding is just 6-7%. That's not very good. Why is that not very good? Think about it. Well, look at the first 2 channels that we use, right? The one from S to A and the one from A to B. We saturate these channels. We fully use them. We assume we can use them. We can take every Satoshi that's in this channel and route it. That's a very big assumption, right? I mean, here, that's not so bad because these channels have 2 Satoshis. But if they have 1 million Satoshis, that probability goes down to 1/1,000,000 if we try that, right? So that's not a very, very good solution. We can do better. And remember, the most probable 1 set path was this one, right through the middle, and it had 36%. So maybe we can extend that. Maybe we can add another path, right? But we have a problem because already here the SX edge, the SX channel is saturated. We can't route anything more about this. So we have no choice. If we want to route more, which we have to do according to flow properties, S2 have to leave S, right? We have to route via SA, and then everything that goes into A has to leave A, right? So we have to route to B. This one is forced. But now we have multiple possibilities, right? How do we go on after B? We could just go on to D directly, like use the edge BD, and that works. And the total probability of all these edges, all these channels, like these multiple paths, which are not disjoint, you see, is 12%. That's already pretty good. It's already almost twice as good as the one path solution. But I'm saying we can even do better. How can we do better? This way. Remember I said now we have to go on from B, right? And the other solution, if we don't go directly to D, is we go down to X. But that's strange, right? Look at it. It's totally counterintuitive because we are already routing 1 Satoshi from X to B, and now we want to route from B to X. What does that mean? Right? We route in one direction and we route the same amount in the other direction. Right? It cancels out, right? It actually cancels out. So we get a solution where this BX channel isn't used at all, even though we used it twice. But they cancel out, right? So the best solution here is this, like the upper path and the lower path, and that is the best strategy. And the question is, well, how do we know that this is the best strategy? I mean, in a simple example, we can just look at every possibility in it, and it works. And that's actually what René was doing in March, thinking about this stuff, finding this method. But but it's really, if it turns out if you want to do this on the whole network, it doesn't work. It's just too complex. There are too many possibilities. Complexity is just too hard. And I listened to him describe that to me, and I said, oh, this is incredible, right? We have something that's very well known in mathematics as a flow, and we wanted to find the most probable flow. It's not possible, as nobody has ever thought about this. It's not possible, right? And it turns out we didn't find anything. Why didn't we find anything? Because it turns out people have thought about something very similar, namely min-cost flows. That is just not most probable flows, but cheapest flows, right? We have a cost function, again, as before, and it turns out people have been thinking about this for a long time, and they have been using it in many areas, right? They have been using it in transportation, warehouses, traffic routing, finance, right? And yes, scheduling time lots and delivering large payments over the Lightning Network. We can actually do that. But if you might be asking, well, why has he been talking about this probability shit all the time when the solution is supposed to be a minimal cost flow, right? A cheapest flow. Well, again, we use this trick that we used before. We convert the probability into a cost, right? That's it. If we're talking about cost here, we're not talking about fees. We're talking about probability cost, minus log of the probabilities. And that works. Then we can actually use these standard algorithms that people have used for decades. And it turns out it's harder to do these calculations than the single path calculations, but it can be done under some assumptions. And it turns out, of course, yeah, if we can do min cost flows, yeah, we might do this for fees, right? Of course, we might also look for the cheapest flows. But that makes things, the question is, why didn't people get to that? And I have a theory. My theory is because it just doesn't work. Because if you try this with just fees, you get really, really bad solutions. Think about it. What's the cheapest flow somewhere? Usually, if it doesn't fit in a single path. The cheapest flow will be the one that first takes the cheapest path and saturates it fully. Again, right? It takes the max amount that it can send along this path. And there's a dwindling small probability that this can actually succeed, right? So we won't get good solutions this way if we just take fees. And there's another reason why this doesn't work. Because the fee structure that we have now in the Lightning Network has base fees and proportional fees, right? The base fee is, you pay for the first Satoshi, you pay not just the proportional fee, but you also pay the base fee, which means the first Satoshi that you route along some channel is the most expensive Satoshi. From there it gets cheaper. But which means the cost function here is something called concave. It goes down in a way. It's bent downwards. And the probability cost that I talked about is the other way around. It's convex, so it's bent upwards. It gets more expensive the more I want to send. And it turns out that this min-cost flow problem can only be solved for convex functions. If you have concave functions, there are some deep results that say this is an NP-hard problem, which means, like for the people who have not done theoretical computer science, it means unless hell freezes over and Bitcoin is worthless and the internet doesn't work anymore, we won't be able to find an algorithm that does this. But we can still do things, right? We could drop the base fee, easy solution. And actually, Siemens has thought about this a bit more. And another thing is, the theorem just says we can't find the optimal solution. But we might find we don't need the optimal solution. We just might find a good solution. And that's better, right? Siemens has thought about this and found a way of doing this where we can still calculate it with the base fees, and we don't get an optimal solution. We get one that overestimates the cost the higher the base fees are. So it gives nodes an incentive to keep the base fees low, because if you put up high base fees, the algorithm will find routes will overestimate the cost of these edges more the more base fee you use, which people just won't use your node that much, right? But you can try. and people have sometimes misunderstood this. If we say drop the base fee, they say, oh, do you want us to route altruistically? No, not at all, right? We just say, we don't think it's very useful. And we actually believe that routing with this algorithm will be very, very worthwhile for the routing nodes, because it gives you a method to price liquidity. Now, what the algorithms now do, they look for the cheapest ways, which means somebody with a shitty node and no liquidity can always beat your price, right? This here depends on the actual capacity, the actual liquidity, which is not fakeable, right? So if you put in the money, you should have a way to raise prices a little, because the cost of probability for your channels is better than that of a shitty node, which might be cheaper but has more probability cost because it's a shitty node. So we think this is actually the incentives here are good, and of course the thing is we still need to optimize for fees, right? I'm not saying ignore fees, which we have been doing so far. Of course, that's really tough, because someone could just say, oh yeah, I'll open a huge channel, everybody will choose my channel, and then I'll take huge fees. So that's not a good strategy. We have to incorporate, we have to calculate with fees somehow. And there, what you do is you kind of make a cost function that mixes these two costs and weights them in a way. And it's not trivial to find these weights, because there's also a result that says, interestingly, even for the single path case, not just for the flow case, for the single path case already, if you want to find a path that's both the cheapest and also it's under the constraint that it also has to have a certain probability, or on the other hand, if you want to find a path that's, say, the most reliable under the constraint that it costs at most this much, that's also an NP-hard problem, even in the single path case. So we can't expect to solve this perfectly, and we can't expect this to be trivial to do. But I think it's very worthwhile to do this, because I think we can. There's a huge gap between, as we saw in the beginning. I think there's a huge gap here. Now it works pretty well to route one Satoshi. It's pretty well to route $10. But it doesn't work to route $10K. And if fees eventually get high on the main chain, we will have to route $10K, and that won't go via one path. So we will have to do this, and it will make the Lightning Network a better place, I think. Of course, we could also use different features, CLTV, latency, geodistance. All the while, we have to make these look convex, because otherwise the method won't work. But this is engineering, right? So, before I close, I will just convey greetings from René again. And as I said, there are several solutions for this min-cost flow problem, or the routing problem in general. Several ways to attack this, and people have already begun implementing several ones. But this is because this is a problem that people have been solving for decades. There are solutions with different trade-offs here, and we're not sure which one is the best. Like, how do you best calculate these things? And so what René is working on right now is find a way to benchmark different solutions, right? Look at the algorithm and see if it's fast, but is it also good? How are the solutions that it finds better than other solutions? And if we find benchmarks, then we could do something like a contest. We could say, oh, send us your trial, send us your algorithm that beats the other algorithms, and then we can have an actual routing contest, and we can find out, we can make real quantified guesses about which one we should use in the Lightning Network. And that's all I have, I guess. Thank you. Any questions? Do we have time for questions?
We have about 5 minutes for questions.
Yesterday there was a great presentation at the end of the day about Watchtower actually, but there was some discussion about the old idea of negative routing fees or dynamic routing fees. Would those kind of advancement eventually completely destroy any reliability of these metrics, even worse than a fixed fees, or they will be more compatible for optimization searching?
I don't see why this couldn't work. I mean, I think it's just as long as everybody knows those fees. It's just the fee structure has to be simple in a way, right? But there's nothing that says they can't be dynamic or negative or something. That's fine.
Any other questions?
Thank you. So do you think if we calculate in probability in the routing fees that we will have even more centralization in the Lightning Network in the future? Because home nodes might be like on the shitty scale of nodes in general?
I think some kind of centralization with the current design of the Lightning Network. I think that some kind of centralization is inevitable, but not in the way that there's one central hub that controls everything. But if you look at how the Lightning Network already works now and how it has grown, it looks like many other networks that appear in nature and in society and in economics and everywhere, and it's called a small-scale network, which means that all these things follow power laws. Right? There are some very big players, and there are a lot of very small players, and there are some in between. But these networks will always look that way, and I think this just makes it more explicit that this. Now, of course, you could. I'm arguing this doesn't really change anything. You could have, of course, you can have thousands of small nodes, but they won't help, right? If there's no liquidity in these networks, of course, people will try them all the time, but it doesn't mean they will actually use them for routing. It's just more failed payments. So I think it's good that if we know where the liquidity is in the network and use this in our routing decisions, and we can. This won't change how the network looks, in my opinion.
Okay. Last call for questions.
There's another one there.
Hi, Stefan. Thank you very much for the talk. My question is, if the protocol switched to having a minimum fee instead of a base fee and a part per million, have you thought at all about the implications of that?
Yeah, that's one thing that's actually possible now already. We have something called a minimum HTLC size that's every node can specify or every channel can specify, and people are doing that. That's an alternative because some people are afraid that if they don't have a base fee, people will just use one Satoshi payments to kind of get away for free. But it's very easy to avoid this by using minimum HTLC sizes. And yeah, I think that's perfectly fine. That works pretty well with the model and with the algorithms, and that's something I think is a good solution.
Okay, thanks, Stefan. We appreciate it.
Thanks.